axial layout of components. Here we have two examples. The top one, we need to design a shaft to support two gears and two bearings. You see the type of gear here. You see the teeth, these ones. If let's say we have an input gear here coming from a motor, okay, force applied to this gear will have two components, axial component and normal component. This axial component, this one, is pushing the gear to the right hand side. So we need to support this gear. We need to make sure that this gear doesn't move to the right or to the left. The same with the other one. The same with this gear. So if we have some other gear here for the output, again, forces on the surface of the tooth are normal force and axial force. So we need to support the two gears so that gears don't move to the left, the right hand side gear doesn't move to the left, and the left hand side gear doesn't move to the right. We can do that by location shoulders. Location shoulders means we design a shaft to look something like this. Okay, different diameters, which is this one. So this is the shaft here. First location shoulder to make sure that the gear, this gear doesn't move to the right, and then another location shoulder, so we make sure the other gear doesn't move to the left. Okay, there's other location shoulders for the bearings also. So the shaft itself is supported by the bearings. So the shaft gets the axial force from the component, and then the bearings support the shaft and make sure that the shaft doesn't move either direction in this example. So this is one way of doing it. The bottom example, here we have a fan and a pulley. In this example, we don't use location shoulders. There is one shaft with uniform diameter, no change in diameter. But what we have here, we have set screws, these ones, for the bearings, for the fan, for the pulley, for everything, set screws. Using these set screws, we make sure that the fan doesn't move left or right. Okay, this to support axial forces. To support torsion, we can put keys, set screws in the bottom example will also provide torsional support for the components. So axial and torsional. In this slide, you see the common means of transferring torque to a shaft and also to support axial load. So for transferring torque, keys are very commonly used with set screws. We can also use planes, we can use bends, we can use shrink fits if the torque is not very high, and also tapered fits. Keys are one of the most effective things to make sure that the shaft and the component form one rotating member, one rotating part, because they slip fit of components into shaft for easy assembly, They will provide positive angular orientation of components, and usually keys are designed from weak material. So for any failure, we make sure that first part to fail is the key itself, not the component, not the gear, and not the shaft. And it will be cheap and easy to replace the key, not the shaft or the component. So to design for stress, we need to evaluate shaft at critical locations. You need to look at the whole shaft, you look at the geometry, you look at diameter, and you look at points where we have stresses, because critical locations are usually locations where there is large bending moment, where there is torque transmission, and where the smallest diameter, and also on the outside surface of the shaft, because stresses are higher at the outside surface, both shear and bending stress. For stress, we in shafts usually we have alternating or fluctuating stresses. So the general formula to calculate normal stress and shear stress must be applied for the mid-range and alternating components. Here you see we have formula for normal stress and also for shear stress. For normal stress, we calculate alternating normal stress and mid-range normal stress. For alternating stress, we use alternating bending moment. And for mid-range stress, we use mid-range bending moment. So if bending moment is not constant, if bending moment is not fixed, if we have bending moment that increase and decrease between two values, first, of course, you know maximum value and minimum value for bending moment. Calculate alternating bending moment, calculate mid-range bending moment, and next step, calculate alternating normal stress and mid-range normal stress. Same with shear. In shear, this formula, if your shear or your torque is fluctuating between maximum value and minimum value, calculate alternating torque and mid-range torque. Next step, calculate alternating shear and mid-range shear. You see here we have stress concentration in all formulas, and that stress concentration will be there if you have point with stress concentration, if you have a change in diameter, if you have a notch, if you have a hole, if you have a groove on the surface, then you need to consider stress concentration for fatigue. Okay, and then these formulas can be customized for round shafts to give you these two formulas. Okay, so now you have mid-range and alternating normal stress and mid-range and alternating shear stress. You learned previously that whenever you have normal stress and shear stress together, you need to combine them in one term. How to combine them? If you remember, distortion energy theory suggests that we use sigma von Mises. Sigma von Mises, and it was sigma x squared plus or minus sigma x, sigma y plus sigma y squared plus 3 tau xy square, and that is under square root. Okay, this is sigma von Mises. We apply it here. If you combine alternating normal stress and shear stress, you will get alternating von Mises. So this will be alternating and this will be alternating, and we don't have these. So this will be reduced to this formula. You see, alternating normal stress von Mises comes from alternating normal stress and alternating shear stress. Same thing with mid-range. Sigma von Mises mid-range comes from mid-range normal stress and mid-range shear stress. Next step is just what you did in previous lecture. Apply the failure theory. You can choose modified Goldman. Sigma von Mises must be used, not normal stress and shear stress, and you just continue as usual. Don't be scared with this long formula. It's just breakdown of what you have at the top. Okay, this is formula for Gerber line, and then all other theories can be applied. Okay, so now here what we can cancel or what we can reduce from the formula. Usually in shaft we have steady bending and torsion. So usually in shafts, bending moment is alternates, but torque is constant. So there is no alternating in torque. Torque is fixed, but bending moment is completely reversed. If this is a shaft and there is bending force here and shear, usually this torque is fixed. So torque is mid-range. There is no increase and decrease. But the bending moment is the same force applied, but because we have rotation, so the point here will go from maximum bending to minimum bending to from tension to compression, tension to compression. So that is mid-range or completely reversed. That means these two values are 0. So this will reduce previous formula. Let's go here. Okay. This will be cancelled. This will be cancelled. This will reduce my equations and to this one. As usual, we always check for yielding. Check for yielding is given by this standard formula. Factor of safety is yield strength by sigma von Mises maximum. So here we use maximum stresses. This is how to calculate sigma von Mises maximum. There is a simpler way on how to calculate sigma von Mises maximum. You simply add alternating to the mid-range stresses to get maximum stress, and then from this maximum stress you calculate factor of safety.